Hey everyone, welcome back. Today's topic is graphing tangent and cotangent. So if we get started by looking at the graph of y equals tangent x, this is the general shape of it, and we get these values just like we did for secant, cosecant, sine, and cosine from the unit circle. So let's take a look at that again real quickly and just refresh our memories as to how we evaluate it for tangent. So here's the unit circle. Tangent, if you recall on the unit circle, is always the y-coordinate over the x-coordinate. So if we start at 0 radians or 0 degrees, our y-coordinate is 0 and our x is 1. 0 over 1 simplifies to 0. So that's why we have a point right here at the origin at 0, 0. If we continue around the unit circle, we don't have to plot anything that's not an integral point. So 1/2 over square root of 3 over 2 would not be an integral point. And with our 4 other graphs, sine, cosine, secant, and cosecant, it was always the quadrant angles that we would graph. But as we continue around our unit circle, if we take a look at 45 degrees or pi over 4 radians, we can see that our x and our y coordinate are exactly the same. And whenever we divide one number by exactly the same number, it always simplifies to 1. So instead of skipping this like we have done in previous graphs, we're actually going to plot a point at 45 degrees or pi over 4 radians, and the y-coordinate would be 1. It's a little bit hard to see on this graph because it goes by 5 on the y-axis, but it would be like roughly here. If we continue around the unit circle, our next point that we would graph would be 90 degrees or pi over 2 radians. And we can see that what happens is we get 1 over 0 for our y over our x, and we can't divide by 0. We're not allowed to have that in our denominator. So we get an undefined answer, which means that we create an asymptote. And that's why we have asymptote here at pi over 2 radians. If we continue around the unit circle, again, at 3 pi over 4 or 135 degrees, we have matching x and y coordinates. Now this is a positive y and a negative x, which means it'll simplify to -1, but a point that we can graph nonetheless. So that would be like roughly here on this graph. Again, it's a little bit hard to see. And if we continue around the unit circle, our next point would be at pi radians or 180 degrees. And if we simplify our y over our x, we get 0 over -1, which becomes 0. So we have a point at pi 0 again. And then we continue, and at 225 degrees or 5 pi over 4 radians, we reduce to 1. So we have a point roughly here. So we were here, and then now here. And as we continue around the unit circle, at 270 degrees or 3 pi over 2 radians, we're going to end up with another asymptote because we'll have 0 in the denominator again. So we create this asymptote. So a period now, instead of being from 0 to 2 pi over here, is actually going to be pi radians or 180 degrees. So an entire period is occurring in about half the time. The points that we need to graph are the x-intercept and then the point at 1 and -1 on either side of it, and then just kind of draw in our squiggle shape, so to speak, that hug our asymptotes, our vertical asymptotes to the left and the right. So in talking about the unit circle, this point actually at 0, it actually starts in the middle of a period. Whoops, that's not what we wanted. In the middle of a period, it starts here. So really the period that you probably want to use from your unit circle would be from pi over 2 to 3 pi over 2. So from here to here, this half of the unit circle would give you one complete period, whereas this side is going to be kind of just a half a period. One thing that we need to talk about is that, like we said, a cycle occurs every pi units. So the first one is from negative pi over 2 to positive pi over 2, and then pi over 2 to 3 pi over 2. So basically every time we have an asymptote, we have a new period. The amplitude there is no amplitude because the graph goes forever vertically and horizontally. But that doesn't mean that there's not a vertical dilation. We can stretch our graph vertically, or in other words, the amount that, or the speed with which it increases or decreases will change. And that is kind of what we think of in place of amplitude. So amplitude is specific for graphs that are sinusoidal, or in other words, in the shape of a wave. Because we do not have that in this case, we don't call it an amplitude, we call it vertical dilation, but it is essentially, for all intents and purposes, the same thing. Okay. We're going to talk in class a little bit more about how to find the equation of the asymptotes, but the asymptotes, because they're vertical lines, are always going to be in the form of x equals, and then whatever the x-intercept is at that point. Because all trig functions go on infinitely to the left and to the right, there is going to be a literal infinite number of asymptotes, but because they repeat in very specific patterns, we don't have to, I can show you how to write it, but we're just going to write that it's basically wherever the first asymptote is plus the period times n, and we'll talk about that more in class in a minute. But the formula for it would be wherever your first asymptote is plus the period times n, n meaning the number of times that you've cycled through, meaning that could be any number. Okay, cotangent is the reciprocal of tangent, so to find it we do the x over the y from the unit circle instead of the y over the x. So we start with an asymptote at 0. So as you can see, the graph of cotangent x has an asymptote right there at 0 on the x-axis. And you can see that it kind of is the reflection of the tangent graph. Here they're both superimposed on the same graph, so you can see what's happening. But it'll behave in very similar ways, in predictable ways, to the tangent graph, but just kind of the reciprocal, or the flipped fraction of it. So again, at pi over 4 or 45 degrees, we're at 1. At 90 degrees now, we're at 0. At 3 pi over 4 or 135 degrees, we're at -1. At pi or 180, we're going to be undefined again, or have another asymptote. So let's just check back in with our graph. We can see that we completed one cycle, and there's our second asymptote. At 225 degrees, or 5 pi over 4 radians, we're at +1 again. At 270 degrees and 3 pi over 2 radians, we're at 0. And 315 and 7 pi over 4, we're at -1. And then we come back to our asymptote again at 0 degrees or 2 pi radians. So again, we can see that if we continue our pattern, we will have another asymptote here at 2 pi radians. You can kind of see the graph approaching it, but never touching it. All of the things about the characteristics of cotangent are the same for tangent. So one cycle is pi units, just like it was with tangent, because we have an asymptote that repeats every pi units. No amplitude, however, that doesn't mean we don't have a vertical dilation necessarily. We could still have vertical dilations. And because we have asymptotes, again, we'll talk about how we write the equations of them, but basically it's always wherever your very first one is, so this one would be at 0 plus whatever your period is times n. So come next class with any questions that you have. These are a little bit trickier than the secant and cosecant graphs that we've done, just because they're a completely different shape. But let me know and we'll talk about it in class and see what the practice will look like. And I'll see you guys then.